Record. Okay, so I made this video where I basically ranted and I taught chemistry, and it was kind of cool, but all the sound got deleted. So now I got to record over it, and also I got really drunk before this, so um, hopefully this is gonna work out. If not, that's cool. At least you got this picture of Migos, or Offset, excuse me, looking through a microscope. Okay, let's do this in one take. That'd be so cool if we could do it in one take. All right, so what did I do? Okay, yeah, so this is a nucleus. Protons, neutrons form together to make a nucleus, and around it, that red stuff is a electron probability cloud. This is a periodic table, and I'm pausing to give myself time to speak. Basically what a periodic table does is it tells you all the elements that we've discovered so far. So whenever a new element gets discovered, it's gonna be plop right there in the periodic table. So let's look at, yeah, carbon 12. Carbon 12 is an element with 6 protons and 6 neutrons. The number 12 is its mass number, which is just the number of protons and the number of neutrons added together. Pretty simple. Also know that a proton has a charge of +1, neutron has a charge of 0, and an electron has a charge of -1. Don't worry what that means. Don't worry about what that means. Doesn't matter. Okay, so this is a atom. This is an atom carbon 12. The green are the neutrons. The black are the protons. The red is actually an electron cloud around it. Because an electron does not act like we act, it does not follow Newtonian physics. It acts as a wave and as a particle. So we cannot know exactly where it is. All we can say is that there's a probability that it is in this space, but don't worry about that shit. That's physics shit. Fuck physics. Okay, let's move on. Come on. How long did I spend on this? Okay. The next thing I'm going to talk about is ions, I believe. So let's wait till my pen looks at that. There we go. Okay, so an ion is a element or a compound that has a plus or minus charge. A cation has a plus charge, and anion has a minus charge. Basically, that means that a cation has more protons than it has electrons, and an anion has more electrons than it has protons. Super simple. I promise you. Draw it out if you're confused. Take oxygen. Oxygen with 8 electrons is neutral. 9, it has 1 extra electron, so it's an anion. 7, 1 less, so it's a cation. Okay, 2 types of bonds. Ionic bond, covalent bond. An ionic bond, like between sodium and chlorine, sodium chloride, or table salt. An ionic bond is a bond where one element rips an electron from another element and forms a bond between them. Basically, this chlorine has stolen a bond, or an electron, excuse me, from the sodium. And now the sodium has a plus charge because it doesn't have as much electrons as it does protons. It has more protons, and the chlorine has a negative charge because it has more electrons than it has protons. Right? Okay, next covalent bond. This is ethanol, CCOH. Ethanol is when we drink, what we get drunk on, drinking alcohol. Covalent bond is a bond that forms when the electron density clouds between two molecules overlap and they share their electrons. So the oxygen is sharing its electrons with the hydrogen to make a bond. Carbon is sharing with the carbon, and with the hydrogens, yeah, that's covalent bonds. So the octet rule is this idea that for an element to be as stable as possible, its outer shell of electrons must contain 8 electrons. The elements that already contain 8 electrons in their neutral state are called the noble gases: helium, neon, argon, krypton, and xenon. And they are ridiculously stable, and every element wants to be like them. Let's take another element. Let's take chlorine. Chlorine, its valence shell, has 7 electrons. And to find out how many electrons its valence shell has, go to the previous noble gas before it, so neon, and count. That's how many electrons it has in its valence shell in its neutral state. So go from neon and you count the elements to chlorine, and it should be 7 elements, which is 7 electrons in its valence shell. So it wants 1 electron, so it can become as stable as argon. So to get this one electron, it is going to bond to something that can give it one electron, like sodium. Sodium, in its neutral state, has one electron. Chlorine, in dire need of this one electron, will ionically bond to the sodium, rip this electron away from sodium, and form sodium chloride. Now, sodium, whose electron is taken away, is even more stable because by losing that electron, it now acts like a noble gas. It has the same amount of electrons that a noble gas does. And, like I said before, every element wants to be a noble gas. Every element wants to be stable. Sodium and chlorine just got really damn stable. All right, this is acid-base chemistry, which I fucking love. So I'm gonna start by going over what pH is, because I think a lot of people have a misconception of what pH is. It's not just that stuff that it's like, oh, 1 pH is gonna burn your hand, 14 pH really basic. pH is actually just the negative log of the concentration of H plus in a solution. H plus is just a proton, so a hydrogen with 1 proton and 0 electrons. And as we know, the scale of pH goes from 0 to 14, and this is just found by taking the concentration, taking the negative log of the concentration. That's going to give you a number from 0 to 14. And for that, you'll find out what the pH is. Cool. So this is an acid-base reaction. Before I start, the red arrows are the movement of electrons. So the base, sodium hydroxide. A base is a compound that wants to accept a proton. An acid is a compound that wants to give away a proton. Proton, once again, is 1 proton with 0 electrons. So the base, sodium hydroxide, it wants to form water. So it takes that proton off the acetic acid, that's the acid, and those electrons, which were once bonded from the acid, from the oxygen on the acid to the hydrogen, go back to the oxygen, and the base's excess electrons form a bond, and that's going to form water because we had OH, which bonds with another H, that's H2O, that's water, and the acid is going to be a deprotonated acetic acid. So yeah, there's going to be a negative charge on the oxygen because it's lacking that proton. So it gains a extra electron, negative charge. Cool. More acid-base stuff. One word you probably haven't heard, pKa. Basically, this is a fancy word for pH. Not actually, but it basically describes how willing a compound is to give up its hydrogen. So let's look. We have ethanol and we have acetic acid again. Ethanol is a pKa of 15. Acetic acid has a pKa of 5. Higher pKa means more basic or less acidic. So pKa of 5 is much more acidic than ethanol. Acetic acid, don't pour that in your hands. Ethanol, you can pour ethanol in your hands. But why? Why does acetic acid have such a stronger pKa? Why is acetic acid such a stronger acid? The answer to this is due to the resonance of the compound. So, what happens in acid-base chemistry? Well, what happens is this acid, acetic acid, loses its proton, forming deprotonated acetic acid, right? And deprotonated acetic acid is able to form a second resonance structure where it forms a double bond, and that double bond to the oxygen jumps up to the other oxygen and forms a negative charge. Basically, it forms the same thing, but on another oxygen. And that ability to delocalize, that's what it's called, delocalize that negative charge increases the stability of a compound. And acidity is directly related to the stability of a conjugate base. A conjugate base is what the compound is once it loses its hydrogen. And a very stable conjugate base is a very strong acid when it has that hydrogen. And because this is able to stabilize that negative charge, it won't pick up another hydrogen and get reprotonated. So it's really strong. It wants to give the hydrogen, and it doesn't really give a fuck when it's gone because it can stabilize that negative charge very well. So it's a strong acid. Okay, one more thing, electronegativity. Electronegativity is the measurement of how strong a atom holds its electrons. electronegativity increases towards the right and up. So fluorine is the most electronegative element. It's an extremely strong element. That's why something like hydrofluoric acid is actually, yeah, here you go. Hydrofluoric acid is really not that strong of an acid because it holds on to that hydrogen really strong and it doesn't really want to give up that hydrogen. And you know, an acid is related to how strong, or how willing it is to give up the hydrogen. That's why something like hydroiodic acid, which is way stronger, even though they're both halogens on the same point of the periodic table, the same column of the periodic table, is much stronger acid because iodine is not as electronegative. It doesn't hold onto that hydrogen nearly as much, and the I negative charge, which is the iodine, once it loses the hydrogen, once it gives its hydrogen away and is no longer acidic, is pretty stable. So once again, stability of the conjugate base is related to strength of acidity. Okay, one more thing, I think. Polarity. Few things about polarity. There is three types: nonpolar, polar covalent, and polar ionic. Nonpolar is when the difference in electronegativity is less than 0.5. Don't worry about these numbers. You can look at a table of electronegativity if you want and figure it for yourself. But something like a carbon-carbon bond or a carbon-hydrogen bond is nonpolar because the electronegativity between those is very low. Yeah, so next is polar covalent. That's like an OH bond or an NH bond, which is, so the difference in electronegativity is between 0.5 to 0.9. That is still a covalent bond, still shares the electrons, but one of the elements is much more favored in where the electron is. So for the oxygen, hydrogen, much more favored. Next, polar ionic, something like NaCl. So when the electronegativity is greater than 1, that's just super polar. One of them, like the sodium in this, the electronegativity is so low and the chlorine is so high that basically all the atoms, or I mean all the electrons are with chlorine. Why does this matter? As you can see on my fingers right now, it matters because say we have this compound right here, which is 1, 2, 3, 4, 5, 6, 7. 7 carbons, long chain of carbons. That's called heptane. Say we have heptane. Say we spilled some heptane on our shirt and we need to get rid of it. What do we use? CHCl3 or H2O? Well, we know heptane is extremely nonpolar because all it has is CH bonds and CC bonds. So we should use a nonpolar solvent like CHCl3. If we use CHCl3, which is chloroform, it's going to eat that shit up and it's going to be gone in a second. But if we use H2O, nothing's going to happen because it's a polar solvent because the OH is a polar bond. It's going to be like if you mix oil and water, it's just not going to mix because nonpolar doesn't mix with polar. And polar mixes with polar and nonpolar mixes with nonpolar. Yeah. What the fuck was I doing? Why did this take way longer? I'm basically done right now. I think. Maybe I missed something. Damn, I hope not. Why was this 3 fucking minutes long? Okay, yeah, I'm gonna explain this carbon chain. So, as you can see, it's like up, down, up, down, up, down, up, down. What that means is that on each of those little like peaks, so the trough, peak, trough, peak, trough, peak, right? That's a carbon, and it, stuff needs to have 4 bonds in accordance with the octet rule. So it's going to have hydrogens in accordance to 4 bonds. So 3 bonds on the carbon, three hydrogens on the carbons on the end, and 2 for every other one because 4 bonds on each carbon. Okay, we're about to finish. So next part, I think. Yes. Okay. Yeah. Cool. So this is synthesis. This is where it's like starts to get real. Like, okay, so you see that compound where the little arrow pointing to the question mark? That's diethyl ether. And I'm asking, how the hell do you make that from ethanol, which is the one down there with the 2-carbon OH plus sulfuric acid? I'll tell you how you make it. So, what do we know about sulfuric acid? We know that it's a really strong acid, and we know that an acid wants to give a proton away. Now, what could act as a base? What about ethanol? Ethanol could probably act like a base. So what's going to happen here is the sulfuric acid is going to protonate, which means gives a proton to the ethanol. And I should be drawing the arrow soon. There we go. And boom, it's going to take that and the electrons from that oxygen-hydrogen bond on sulfuric acid is going to go to the oxygen of sulfuric acid, forming the sulfate ion, which doesn't matter. It's not reactive at all. It's super stable because, sulfuric acid is a strong acid. And, this reaction is going to take heat to actually work. But once we add heat, it's going to form protonated alcohol, which is an alcohol with 2 hydrogens bonded to it. This is actually pretty acidic, but it's also really unstable because it doesn't want that positive charge in oxygen. It doesn't want that shit. So what's going to happen? What's going to happen next? How are we going to form diethyl ether from this? All right, I'll show you how we're going to form diethyl ether from this. We're going to take the other molecule of ethanol, because there's still ethanol in solution, and that ethanol is going to attack this other protonated ethanol we made, which is the ethanol with the plus on it. And watch. I will draw it right now. Nope. Sometime I'm going to do it. There we go. So that's going to attack the carbon that the oxygen is bonded to, and it's going to bump out the oxygen. Oh, yes, this is called SN2, but don't worry about that. That's just the name of the reaction. And this OH2 is now going to be bumped out, and OH2, what is that? Oh, that's H2O, that's water. So what's going to happen is we're going to form water, and we're also going to form this substitution. That's what happens when a chemical is substituted for another chemical. A substitution product, which is going to be the protonated diethyl ether, which I will draw in a second. Boom, with the oxygen and 2 carbons coming off of that, and hydrogen, and that's going to be protonated. Boom, boom. There we go. Look at that. Don't know why I drew a circle around the cross, but it doesn't really matter. That is not diethyl ether yet, because it still has the hydrogen bonded to it. So how's that going to go away? Oh, what about the water we made when we kicked off the water group from the protonated alcohol? Oh yeah, that could act as a base. There we go, H2O, bum bum. That's going to come, excuse me, and that's going to take that hydrogen from the protonated ether. Oh, and ether, by the way, is carbon. So carbon chain, oxygen, and then a carbon chain coming off the oxygen. That little bird is an ether. There we go. And that's going to take hydrogen and form diethyl ether. It's going to form that compound. Yeah. Cool. You guys learn how to make a drug. Go have some diethyl ether. Okay, well, I bet now, still, some of you guys are like, okay, that's fucking cool, but I don't give a shit about this stuff. Why does this matter to me? I'm going to show why it matters to you with this actual example that's affecting your life every single day. But if you didn't know anything about chemistry, you wouldn't know why the hell it was affecting your life. All right, you see this molecule, this S with the 3 O's coming off of it with the double bonds. Those are the 2 lines coming to the O's. That is sulfur trioxide. That is a pollutant that is released when you burn coal. That's just like a fact. That's just when you burn coal, that's going to come. But if someone's like came up to you and said, "Oh shit, we need to stop burning coal because sulfur trioxide," you'd be like, "I don't fucking give a shit about sulfur trioxide. Who gives a fuck about that shit? It sounds like some dumbass shit." But you'd be wrong, because what is in air? Oh, water. What happens when water hits this compound? Oh, I'm going to show you what happens, and you'll know, if you know chemistry, you'll know why this stuff is bad. Okay, what's going to happen? So, the water in the air, that's going to come, and it's going to attack the sulfur, right? Because sulfur can't form another bond. It's going to form an oxygen with a minus charge. Don't worry if you don't understand that. That's just chemistry shit. That's organic. Anyway, that's going to get deprotonated because we have the water that bonds on, which was O and H2. It's going to be protonated. Water's going to come and it's going to deprotonate. It's going to act as a base, and then the oxygen is going to get reprotonated. And basically, what's going to happen is we're going to form sulfuric acid, which is, an awful chemical. You don't want that anywhere near you. That shit will eat through your skin. So burning coal forms sulfuric acid. And would you know that if you didn't know anything about chemistry? No, I don't think you would because you wouldn't really understand what happens in our atmosphere that causes this random chemical to make acid rain and I don't know, ruin environments and ecosystems. I don't know. That seems important to me. That seems like a reason you should learn chemistry, so you know that the world is going to shit. Hmm. I think I have one more. I think my next one is about water fluorination. It's coming up. I got the thing right now, so I know when it's coming right now. Okay. Yeah. This is water fluorination. One of those stupid ass myths that the government is trying to control you through water fluorination. No, they're not, because if you knew anything about chemistry, you know why the hell we put fluorine in the water. Uh, I can tell you why, because, okay, the chemical on top, that's what your teeth are made of normally. You see that oxygen? The OH group. Um, what water fluorination does is it switches that OH group with a fluorine. What's so good about that? Well, as we know, what happens when you have an OH group and an acid? So, like, say you're drinking Coke with citric acid in it. What's going to happen? Oh, it's going to just protonate that OH group on your teeth, and then that's going to form water. Whenever I draw this arrow, come on, arrow. There you go. That's going to form water. I'm just going to form it. I'm just going to write it in red pen because I don't give a shit. Yeah, that's going to leave as water. That's going to that's called tooth decay. That's called tooth. You don't want that. Fluorine though. Fluorine's not going to do that. Fluorine doesn't give a fuck. Fluorine's super stable, all bonded. It doesn't want to leave. It doesn't want to get out of there. It doesn't want to form water and bounce. Fluorine don't want no proton. Fluorine don't give no shits. Fluorine's stable. Would you know that though? Or would you know that if you didn't know chemistry? I don't know. Or would you think there was a government conspiracy? I don't know, dude. I don't know. I'm getting drunk. I gotta go to bed. Yeah. Stay frosty, my friends.